So let's start at the beginning. In 1925, a physicist named Erwin Schrödinger, yes, the same guy famous for the cat thought experiment. Yeah, it's pretty interesting. You should check it out. Was trying to solve a massive problem in physics. Scientists knew that electrons had wave-like properties, but they didn't have an equation that described how these matter waves behaved. Schrödinger, probably saying that incorrectly, excuse me, Schrödinger sat down and he developed an equation that became the foundation of quantum mechanics. And here's what's amazing. It works. Like it really works. It predicts the colors of fireworks, why metals conduct electricity, how lasers function, uh, why the sun shines, and basically all of chemistry. Every single chemical reaction you have ever heard of is electrons rearranging themselves according to Schrödinger's equation. Now, I'm not going to write out the equation with all the symbols because that's not what this is about, but I'll tell you what it does. It gives us a mathematical function called a wave function. Think of it, think of it like a recipe that tells us the probability of finding an electron at any point in space, not where the electron is, because bizarrely, it doesn't have a definite location until you measure it, but where it might be. So how do we solve it? Here's the thing about the Schrödinger equation. And why am I even talking about this? I'll get into that in a minute. Schrödinger equation, it's what mathematicians call a differential equation. That means it involves rates of change. And solving it isn't like solving, say, x plus 2 equals 5. It's more like imagine someone tells you, I have a function, and when I take its derivative, I get back the same function. What function could that be? Well, that would be an exponential function. Schrodinger's, I keep messing that up. Schrodinger's equation is similar, but let me tell you, way more complex. For most atoms, you literally cannot solve it exactly. The math is just too damn hard. Even with modern supercomputers, right? We can only get approximations for anything more complex than hydrogen. But hydrogen, beautiful, simple hydrogen, just one proton and one electron, we can solve exactly. We can write down the complete mathematical solution in a form that looks complicated, but is actually just algebra with some special functions, right? And that's what this visualizer does. I'm going to show you that here in a moment as you're staring at my Visual Studio Code. It takes those exact mathematical solutions and turns them into something you can see and interact with. The project isn't 100% complete, but I don't care. This is a learning process. Talk about notes. My inspiration for this project you are about to see was a YouTube video that I saw. It was a professor on this very topic, the Schrödinger equation. Am I going to continue to mess that up? Excuse me. I'm probably not saying it correctly anyways, but the YouTube video was a gentleman talking about the Schrödinger equation and hydrogen, and it was fascinating. And I thought, I've got to do something with this, whether I can get through it or not. Anyway, you might be wondering, why hydrogen? Why not oxygen or carbon or something more interesting, more cool, right? Well, here's the deal. Hydrogen is the only atom we can solve perfectly. Think about it this way. With hydrogens, you have one electron being attracted to one proton. That's a two-body problem. And we have known how to solve two-body problems since Newton. It's like the Earth orbiting the sun. Complicated but solvable, if that makes sense. But the moment you add a second electron, say like in helium, right? Now you have three bodies, one nucleus and two electrons, and those two electrons repel each other because they are both negatively charged. Now you have to account for the nucleus attracting both electrons and the electrons pushing each other away. Get the hell away. The math becomes impossibly tangled. It's a mess. So hydrogen is our perfect test case. It's the foundation. If we understand hydrogen, we understand the basics that everything else builds on. Plus, hydrogen makes up 75% of the universe's normal matter, so it's kind of important. I'm going to, this is VS Code, clearly VS Code, and there's a lot of code in VS Code. Let's open this up. Quantum Orbital Visualizer. It's an interactive 3D visualization of hydrogen atom wave functions. Now, it's not 100% complete, but I'm going to show you what I have so far. It's a little too close for comfort. Okay, well, let's get to a comfortable. Yeah, that looks okay. Can move it around. I'm just going to leave it right about there. Okay, so when we solve the Schrodinger equation for hydrogen, we don't just we don't just excuse me, we don't get just one solution. We get an infinite family of solutions, and each one is labeled with three numbers. These are called quantum numbers, and they are like an address system for where electrons can be. Think of it like this. If I want to tell you where someone lives, I might give you a city, a street, and a house number, right? Quantum numbers work the same way. They specify, excuse me, which orbital or probability cloud the electron occupies. Principal, let's get into this a little bit here. Right here, if you can see this over here, the principal quantum number. The principal quantum number, and in this visualizer, it goes from 1 to 7. As you can see here, see, 1 to 7. This number determines two things, the energy of the electron and roughly how big the orbital is. I'm going to go to 3. Well, let's go to 4. Let's go to 5. That. Make it a little bit bigger. I like that. I think that's good enough. Let me give you a real world analogy. Imagine a parking garage with different levels. The ground floor costs the least to park there. That's like n equals 1, right? The ground state, the lowest energy. The second floor costs more. That's n equals 2. The third floor costs even more, n equals 3, and so on and so on and so on. In the in the hydrogen atoms, talk a little bit. When n equals 1, the electron has the lowest possible energy, say negative 13.6 electron volts. The negative sign means it's bound to the atom. It would take 13.6 electron volts of energy to rip it completely away. When n equals 2, the energy is negative 3.4 electron volts, higher energy, less tightly bound. When n equals 3, it's negative 1.5 electron volts. Now, angular, let's see, do I want to, let's jump right into angular momentum. This one right here. So angular momentum quantum number. The second quantum number is 1, and this one determines the shape of the orbital. Here's where it gets interesting though. You know how in chemistry class you learned about S orbitals, P orbitals, D orbitals, and F orbitals. Those letters are actually code for the value of 1. When 1 equals 0, we call it an S orbital. It's spherical. When 1 equals 1, we call it a P orbital. It's shaped like a dumbbell or figure 8. Uh, let's see. Let's do. It takes a moment. Okay, this is a little more interesting. I think I like this a lot better. We'll leave it right there. Yeah, I'm gonna leave it right there. And so when one, let's see, where is it? One, two, one, two. When when one equals 2, we call it a d orbital. It has more complex clover leaf-like shapes. When 1 equals 3, we call it an f orbital, extremely complex shapes. Let's go ahead and change this again. It takes it a moment. Check that out. Isn't that cool? It's really interesting. Let's change it again. Give it a moment. Oh my gosh. That one is my personal favorite. Let's change it again. That's pretty cool, but I have to say, I'm going to go back to this one. This is my personal favorite. Oh, yes. I like, oh, that is so cool. Okay. Now there's a rule. One can't be bigger than n minus 1. So if n equals 1, then 1 can only be 0. That's why we have a 1s orbital, but there's no such thing as a 1p orbital. There isn't enough energy to support angular momentum. But if n equals 2, then 1 can be 0 or 1. That gives us 2s and 2p orbitals. If n equals 3, we get 1 equals 0. Yes, 1 or 2. That's 3s, 3, 3p, and 3d orbitals. I may have messed that. And 3, yes. Okay, let's let's move on to a magnetic quantum number. Let me talk about what this is a little bit. The third quantum number is m. So you can see there's m. And it determines which direction the orbital points in three-dimensional space. It's called magnetic because if you put the atom in a magnetic field, these different orientations actually have slightly different energies. The field picks out a preferred direction, but with no magnetic field, they all have the same energy. So here is the rule. M can be any integer from -1 to +1. So if 1 equals 0, an s orbital, we can we can only M can only be 0, excuse me. Makes sense. A sphere looks the same no matter which way you rotate the thing. If 1 equals 1, a p orbital, M can be -1, 0, or +1. That gives us 3 p orbitals, all the same shape, just pointing in different directions. These are the px, py, and pz orbitals you might remember from chemistry. If you didn't, you know what? That's cool. That's fine. If 1 equals 2, a d orbital, m can be -2, -1, 0, +1, or +2. That's 5d orbitals with different orientations. I know it's a lot here. Um, let's do, I'm going to show you a little bit more of this. There's a lot more I want to talk about, but I don't want to go on and on. I've already blabbed enough. Really, really my biggest, like I said, my inspiration for building this is I wanted to see just what I could. Look how that changed. Isn't that amazing? That is so cool. Just like I was talking about. Let's do positive. Let's do positive too. Whoa, I like that. That's really neat. That's cool. Let's do negative. Let's do -3 in the magnetic quantum number. Oh, that is. Oh, I like that. I like that right there. That's really, really cool. I'm liking that quite a bit. Um, and oops. Let me fix that. Now I've got some energy. I got an energy levels graph down here showing the hydrogen atom energy levels. It's really cool. A radial probability distribution graph down below here. I also have an angular distribution graph. I have a probability heat map. Some of my lettering is not fit in the box, but I can fix that later. Here's the statistics quantum state properties box. I can go into visual. Now I do need to make some adjustments here. Here's my ISO surface level, which is cool. I'll show that here in a moment. Grid quality, I can do low, medium, or high. I currently have it set to medium, low, medium, high. Visual theme, you can't really see it. I need to go in and make a fix. Did it not? Okay, give it a moment here. Cool. So I can change the theme. I was thinking, why not have a cool matrix like green-esque look? And then render mode. I know this still needs some fixing. Yeah, I still need to work on this a little bit. Let me do this high. I don't think we're going to see a lot of difference with the high grid quality here. Am I tripping? I feel like that may look a little bit better. I don't know. Either way, there it is. And then I can go to the superposition builder. I'm still kind of working on this a little bit. Let me check my notes and see if I have any messy ass notes I can read about this. Uh, yeah, I mean, I do talk about the Heisenberg uncertainty in my notes a little bit. I don't want to get into that though, although it is interesting. It is interesting. So, I mean, I can change this around a bit. Coefficient, see, I can create superposition. Superposition created, and it gives you some values here, which is kind of neat. I also have a measurement tool here that you can play around with. Oops, you can move this around. And then you can calculate. You can give you a calculation. I can change the point probe. So some of this is not 100% in working order. I can calculate this. Okay, and it gives me this as a result. I'm not going to go on and on into that though. And then I'm currently working on a game integration. It's going okay. I can choose, you can't see it, or maybe you can. I've got orbital matching, probability hunt, a speed run, and then I can just randomize it and whatever. For example, I can do a speed run if I want, start challenge, and then oh, I like the way this looks in this theme. That looks pretty cool. But you see, it is not 100. It's not 100% done. If I do a probability hunt, start challenge, it's going to give me this. It doesn't matter what I select. If I select this, for example, submit answer, nothing's going to happen yet. I will hopefully get it done. And then up here you can choose between easy, medium, hard, or expert. I think I'll stick with easy once I get it going. I'm not gonna lie there. And then I've got a help tab here, a quick guide, quantum numbers, render modes, and tips. Let's go back here. Let's see. Let's play around with this just a little bit more. It always takes a moment. It's got to think. Let's bring this down. Oh, yes. This down. Okay. Did I break it? I think I broke it. Yeah, let's see. Here we go. Magnetic quantum number M must satisfy. Okay. Visual. I am playing around here. Okay. I'm gonna play around here. All right. A little bit of playing around with it. It's a learning process, you know. I've really enjoyed this. 100%, not yet, but I'm learning a lot, and that is, I just love it. I love it. I love math, physics, chemistry, and I'm just a nerd, and this was fun. So that is that. My next project, I'm really excited to show. It's not a science deep project. It's more of a um, well, you'll see. It involves roof tiles, and just leave it at that. And there it is. I have to change this one more time. I'm going to bring this down to 5, principal quantum number, angular momentum quantum number, and your magnetic quantum number. I love this stuff. Takes it a moment. As soon as this comes up, I'm going to end it. Bam, boom. So there you have it. The Schrodinger, I do this every time. The Schrodinger equation solved analytically for hydrogen, visualized in real time with every single detail, for the most part, correct, down to the mathematical foundations. I tried. I did my best. It was a good time. This is quantum mechanics, probability clouds, wave functions, superposition, uncertainty. It's weird. It's weird stuff. It's counterintuitive, and it's absolutely experimentally verified as the way reality works at the atomic scale. And that's all I got for you. Thank you for watching the video, and I will see you in the next one. See ya.